took a look at the outline, and I've marked in red those items which we discussed last time. They're marked with number 1, so since we don't have color, they're the ones we talked about last time. The items marked number 2 are some of the things I want to touch on today. I want to talk about the matrix formulation, the boundary conditions at interfaces, what do we mean by guided waves, and in particular take a look at surface waves as a special example. And then I also want to go briefly and talk about layered structures. Now, recalling what we were doing the other day, let me also just project for you a picture of, you're going to zoom, what we call a slowness surface. This is just a Cartesian plot of the reciprocal of the velocity, reciprocal for reasons which we might get into later on. But what you can see here are 3 contours, one corresponding to a quasi-shear solution, another one, another quasi-shear solution, and a quasi-longitudinal solutions. At any direction, these are with respect to x and y, so the plane of the surface is normal to the z-axis, and we're plotting the slowness as a function of the orientation in that plane. And at any direction, what we do have is 3 velocities, as we discussed last time, and each of these velocities has an associated polarization, and that's what's indicated on those diagrams. This is taken from the first volume of Old, and if you want to look at some of these, you can either get it out of the library or borrow it. Now, some of these contours can take on some rather dramatic shapes. This is, for example, the slowness curve for tellurium dioxide. We call the reciprocal of the velocity the slowness. And so you can see that we can have some very dramatic features. This one happens to have a pure shear, which is polarized perpendicular to the to the surface that you're plotting on, and it doesn't matter what direction you're at. The others, however, undergo some fairly radical changes in velocity as you go around this particular plane. I don't want to dwell on this, but some of these pictures are worth taking a look at and give you a certain amount of insight into what is going on. So let's go back now. The sheets which just have words on them are I think I'm zoomed here. I had better unzoom. That looks okay. The matrix formulation is one of the main things I want to talk about today and see how it is applied eventually to layered problems. Now, let's talk about previous formulations first of all. Previous formulations have tended to reduce the number of variables to describe the problem to a minimum number. And for piezoelectrics, this is 4. For non-piezoelectrics, it's 3. And what you end up with is a second-order system in 4 variables for the piezoelectric case. That's the underlying, what we might call the wave equation, the equation of motion, once you've decided you're looking only at sinusoidal steady-state problems. And so that's the way which had been used up to relatively recently. And what the matrix method does is, instead of developing a second-order differential system in 4 variables, develops an 8th-order differential system, which is first-order differential system in 8 variables. So we go from 4 variables to 8. We go from a second-order differential equation to a first-order differential equation. The advantages here, I will stress as we go along, are twofold. First of all, first-order matrix differential equations form the backbone and the bread and butter of system theory. And so there's an enormous body of knowledge and numerical algorithms and understanding of the properties of linear systems of that kind. And so it turns out that that is important and allows you to simplify tremendously some of the computational work involved in surface wave problems, and in particular in multi-layered problems. So the variables that we will choose are the three particle velocities, which I call V1, V2, V3, and wherever you see 1, 2, and 3, you might sometimes see X, Y, and Z. I use them interchangeably, and I'll explain what this is. The three stress components, that's T31, T32, and T33, this would have been written as a vector T suffix Z in some of the notation that I talked about last week. In addition, because it's piezoelectric, we need two electrical variables, and there you have a certain amount of freedom. I choose the electric potential and the normal electric displacement. By definition, as I will show you what my preferred geometry is on the next sheet, I always take the z-axis as perpendicular to the surface under consideration. So T31, T32, and T33 are the things that would be zero if we had a free surface, and the things that have to be continuous if we had two surfaces in true mechanical bonded contact. The electrical potential then and d sub 3 in fact define the 8 variables we're talking about. We have 3 velocities, 3 stresses, 1 potential, and 1 electric displacement. Now, it can be shown that you don't need any more variables than those 8. Any other variable you want to compute can be uniquely expressed as linear combinations of these 8. Of course, for the non-piezoelectric problem, this simplifies to 6 variables, just the stresses and the velocity. By the way, the transparencies, again, which have words on them, are ones that I handed out the other day. So you can follow those. The next thing I want to take a look at is a little more closely, what are the boundary conditions that we are going to be dealing with. And so here we have the, on the right-hand side of the picture, I'm showing the coordinate system. The z-axis is normal to the surface. I'm showing a layer on a half space. The direction of propagation will be the x-axis. So depending on the notation you use, this could be the x-axis is the x1 axis, the z-axis is the x3 axis, or I can call it the 1 axis and the 3 axis. There is a certain amount of redundancy and interchangeability between using those particular words. So I'm then considering now a whole group or a whole class of problems in which I could have an infinite half space, which is the standard surface wave problem. We could have finite thickness plates, which would be for plate resonators, for example, and combinations, of course, of multi-layered half space with one free surface, and that, of course, is what is shown on the top right-hand corner of this particular sheet. Now, the thermodynamics and the fundamental mechanics of the problem, and I say electromechanics because we also have electrical variables, require that these variables which I set up to be the variables I will use in the analysis are precisely the variables that have to be continuous at interfaces. Wherever you have interfaces between two media, you have in the electromagnetics continuity of the tangential electric field and the normal electric displacement. Here, instead of the tangential electric field, I'm using the potential. They are actually equivalent. So we're using exactly what you would do if you were solving a microwave field problem. The mechanics, though, we have to have continuity of those 3 stresses as 3 stress components and the 3 particle velocities. Please don't confuse the V1, V2, V3 They have nothing to do with phase velocity. They're just the particle velocity, the velocity of the moving particles in the medium. Sometimes we therefore have, wherever we have a mechanical free surface, we have to have the three stresses that I've labeled go to zero. The particle velocities must be continuous, and the electrical potential must satisfy Laplace's equation, so has the normal component of D3, unless we have a very thin short circuit, a short circuit of zero thickness on the surface, in which case for the piezoelectric problem, the potential also must vanish. If you have a metal, of course, you have a discontinuity in the normal component of D3. The difference between what's in the insulator and on the metal surface is, of course, the surface charge density. So that's fundamental electromagnetics, and we have to satisfy the mechanics and the electromagnetics for this problem, because we have this medium that supports both electrical fields and mechanical fields coupled together. They're not separate. So that's sort of the background and what we have to watch out for in solving any mechanical problem, any electromechanical problem, which does have boundaries. And what I want to talk about now is the fact that boundaries are the things which produce the guiding. It is because of boundaries that we have guiding, and if we have more than one boundary, so that there's maybe a thickness involved in the problem, we have dispersion. Okay, so let's just take a look at that. The guiding is the fact that in order for a wave to be guided, the energy somehow or other must be concentrated somewhere. The somewhere is usually the free surface or an interface where you have a geometry such as the one shown at the top right. Now, because of guiding, we now have two of the partial derivatives do not vanish. Remember, with bulk waves, we had ddy and ddz both vanish. Once you have guiding, there has to be a transverse variation. We don't know what it is a priori, but we have to allow for it, so we put a d by dz, which is not zero. And of course, since we are looking for wave solutions in the direction x1, or x, then d by dx is just minus j omega over the phase velocity. I don't know what the phase velocity is, but if it is a wave with sinusoidal frequency omega, then it has to propagate with some phase velocity, and d by dx then by definition has to be minus j omega over v subscript p. So that's sort of what you build in before you do any significant additional analysis. So here are some characteristics that I can talk about. A plate of finite thickness, for example, has two free surface boundaries. We have two surfaces. There's an upper and a lower surface, so that the resultant plate wave will have dispersion. Now, what dispersion means is that the phase velocity will depend on the radiant frequency. And the dependence is extremely complicated in general, and it will exist whenever you have a problem in which we do have a finite dimension involved. In this case, for example, we have a thickness h, and so we will have a solution in which, depending on the velocity that we assign to the problem, we will get a different phase velocity, and that's what we mean by dispersion. In addition to that, whenever we do have guided waves with dispersion, we almost always have many modes which are possible. In other words, there are many guided modes that can be supported by a free plate. And we will talk a little bit about that a little later on. For plates of finite thickness, just a single plate, there are always 3 all-pass modes. By an all-pass mode, it means that the velocity as a function of frequency continues asymptotically as the frequency tends to 0. So technically, DC is permitted. And that's for a plate. The half-space problem has just got one boundary. You just have an upper surface. If we have no layer, then what we end up with is the well-known result that the surface acoustic wave velocity is independent of frequency, and so this is a problem in which we have no dispersion. Now, I want to say 2 additional things with respect to surface waves. In addition to the normal lossless, non-dissipative surface wave solution that exists, we find that there is at least one non-leaky surface acoustic, there is at least one non-leaky surface acoustic wave mode. That's what we call the standard surface acoustic wave solution. But there may be 2 other pseudo surface acoustic wave modes. I'm not going to discuss pseudo modes today, and I will leave that to a later talk. But I do want to mention it over here. Moving on to the problem where we have multi-layers, and multi can be as little as 1. This is 1, for example. Such problems have always got dispersive solutions. The velocity always depends on the frequency, and in addition, there is always more than one mode. Okay, now, depending on the thickness and frequency that you're working at, will determine how many modes at that frequency may exist and may propagate without loss. So that's sort of the general words that go as a follow-on from the bulk wave problem. To recap, in the bulk wave problem, we have ddz equal to 0. We have no dispersion, we have 3 velocities, and that takes care of that problem. And there are explicit ways for calculating what the velocities are and what the wave polarization is. For the guided wave problems, we do not know a priori what the phase velocity is going to be for a given frequency. And how you handle that problem and how you solve that problem is something I want to move on to next. Are there any questions on the things we've said, or the things I've said until now?
When you say always multimodal, do you mean, are you referring to the cutoff modes?
I'm referring to the fact that there is, in general, for an arbitrary choice of frequency, there may be many modes which can propagate without loss. There is always the, quote, lowest order surface acoustic wave type of solution which exists, and that one extends to 0 frequency. On the other hand, the higher order modes only come in at a critical cutoff frequency. So as you go higher and higher in frequency, you have more and more permitted lossless propagating guided modes. And that's, yes, Majid?
Yeah, I guess because the modes are a function of geometry, but for every given frequency. So you can have multi-modes at one frequency and the number of modes will be totally different between each change it.
Yes, well, you can either have fewer or more modes.
Right.
Usually as you go higher in frequency, you start picking up more modes.
When it comes, if dispersion was the main issue, if I have the choice, let's say I have the choice between two geometries, would that be better to increase the number of modes anyway, as far as dispersion is concerned, if I have to live with a lot of modes, wouldn't I be tempted to maximize the number of modes to reduce dispersion?
No, because each mode individually is dispersive, and each mode has a different shape to its velocity versus frequency characteristic. So it's an interesting question that you ask, but I don't know even how to start thinking about what am I going to do about it, or what can I do with it. It's wide open. That question is wide open, yeah. Okay, so let's take a look then, and with the constraint now that we do have guiding, I repeat then that we have d by dx and d by dz are not zero now. And so when we look at the translational equation of motion, which we looked at last Monday, in addition to a d by dz term, we have a d by dx term. So last time when I was talking about propagation in the z direction, I said d by dx is 0, and this is all I had for my translational equation of motion. I now have another term. So although technically it becomes more complicated, conceptually we are still dealing with the same key constraints and relations, namely the electrodynamic equations of motion and the properties of the medium. Well, if you go through the things we did last time and retain both these derivatives as non-zero, you end up with this is what happens to the equation of motion, and the strain relation can be written as these two equations. And now you see I have, in addition to the matrix gamma 3,3, which we had used and identified the other day, we now have a bunch of other matrices whose definition I will come to just a little bit later on. And of course, for the purely mechanical problem, this is a mechanical problem. I don't have any electrical variables, because just the bookkeeping of keeping track of those starts to hide the critical issues we're talking about. So at this stage, I'm just looking at things for non-piezoelectric. So we have these equations, and since it's non-piezoelectric, this is really 3 equations, that's another 3, and that's another 3, so we have lots of equations. In fact, we have too many equations, because for the non-piezoelectric, the number of variables we need is just the 3 stresses and the 3 velocities. So what we're going to do here is get rid of the vector t sub x, okay? So in these equations, we're going to get rid of t sub x there, t sub x here, and we also are going to set d by dx is minus j omega over v sub p for x propagation. All right, now I'd like you to do it in your own time at some later point, just so that you're sure you're following the steps that we are dealing with here. And so proceeding then, when you do that for the non-piezoelectric, it turns out that you can write everything you need as the matrix which is pointed to by that arrow. And you'll notice that what we've done here is we've kept the t sub z vector and the v vector, so that's 6 variables. Same on the right-hand side, and I now have something of the form d by dz of a vector is equal to some matrix times that vector. And that should please the systems people here no end, because that is a standard zero input type of statement that people are probably familiar with in the time domain. This is, however, a spatial domain statement. Now, this matrix A is a function of the phase velocity, because we're going to be setting d by dx is j omega over v sub p, so that's going to come in somehow. And there's a j omega that stays out front. And this particular matrix, I'll show you what it looks like. And I think you all have that sheet as well, so you can see it from where you're sitting. And again, I'd like you to show it. See if you can do the little algebra that's needed to express, to show that this matrix A is indeed this one here. Remind you that the big vector X, big matrix X, is the matrix gamma 3,3 inverse. It appears in a number of places here, and it's sort of important. Take a very careful look at this matrix A, because the only thing in it that is not a material constant and is not known is the phase velocity. Secondly, it's the identity matrix, the third order identity matrix, okay? Because each of these blocks are 3 by 3, and so I have a diagonal matrix of row of 3 rows. So that's what happens when we are in fact talking about guiding problems. Any questions here? There's a lot of information in here, but for the non-piezoelectric case, it's not too tricky, and most a little bit of effort will allow you to just go over this material relatively quickly. Yeah? No, 6 by 6, because TZ is 3 elements. T31, 32, 33, and there are 3 particle velocity field components, V1, V2, V3. So the equation which is pointed at by the arrow, d by dz, that's a 6-component vector.
Right, that velocity equation, A, I don't see pi. I agree.
No. This is 3 by 3, this is 3 by 3, it's in block form. This is in block form, okay? You might want to make a note of that. This is 3 by 3 blocks.
And does the order of matrix multiplication make a difference? That's the correct order? Or does it not matter?
No, the way this is constructed is very important. Otherwise, if you would be talking about an interchange of the upper and lower half of the vector. So you have to, when you do the algebra, that's how it will come out.
Okay.
Mm-hmm. Any other questions? Do you have any questions from the control room? Okay, what I want to do now is go over the second package of sheets, which sort of outlines a little bit, in a little more detail, what we're doing. And I'm going to talk about it for the piezoelectric situation. So for example, we now, in addition to the T sub 3 and the V, I've included the normal electric displacement and the potential. It's useful and simplifies the problem formulation, instead of using the potential, to use j omega times the potential. Okay? This is just a convenience which allows me to take out the j omega from the matrix, outside the matrix, and that turns out to have some simplifying consequences. If we have a free surface, the vector T sub 3 must vanish. If we have a shorted surface, the vector j omega phi must vanish, and all the others have to be continuous. The assumption, the basic assumption, is that we are propagating in the x1 direction, and that any interfaces are normal to the x3 direction. You see, I've switched from x, y, z to x1, x2, x3. I hope that's straightforward. And so a wave function will just go as j omega bracket t minus x1 over v sub p. So v sub p is the phase velocity in the x1 direction. And as we just took a look at a moment ago, all of this can be written as the derivative with respect to z, or with respect to x3, as I have it here, as j omega big A tau. So tau is this 8-component vector. For the non-piezoelectric, it would be the 6th component that I had just had on the previous sheet. And of course, now the structure of A will be a little bit different from the one that I showed earlier, but not much. And from system theory, we know that a matrix differential equation of this form, first order matrix differential equation of this form, has the solution that its value at some arbitrary location x sub 3 is equal to the matrix exponential of the coefficient matrix of the vector times tau at your reference point, your origin. This matrix exponential is known as the state transition matrix in system theory when you're dealing in time domain problems. And its properties are very nice. Its determinant is unity. Its inverse is just the same thing with a minus sign in the exponent. And there are lots of good things known about that type of matrix. And what this is a mapping. It maps the value of these 8 components from some location to their value at a different location by this exponential matrix. This is in fact a transmission matrix, and you may think of it this way. However, bear in mind that this is a transmission matrix in the z direction, or in the x3 direction. It's not a transmission matrix in the direction of propagation. So this tells you something about how the stratification enters into the problem. The propagation direction is completely defined by the statement that we have a wave traveling with velocity v sub p. That's all we need to say. Any questions on that? So now we can go and push this a little bit further. I guess we'll move it off. And forgetting the details, here is what we had just the sheet before. The only thing is, it looks exactly the same. However, the gammas in here are now, instead of being 3 by 3, are 4 by 4, and the gamma matrices are defined by equation 4. And this is where you see where piezoelectricity comes in. The upper block here is exactly what we had in the non-piezoelectric problem. The addition of the electrical variables introduces 3 piezoelectric constants, little e's, and they're over here, and a permittivity. This is the electrical permittivity of the material. Symbolically, this matrix looks exactly the same as the one we looked at on the preceding page, with one exception. Instead of having the density times a third order identity matrix, what we have here is a 4 by 4 matrix which has an added 0 in the 4th row and column. That's the only difference. Everything else here is null. So there is a small difference, and as long as you use this definition for the gammas and this for the big matrix A, then you have your problem properly formulated. This is the dynamics of the situation. And again, what don't we know? We don't know the phase velocity. What is the phase velocity? Well, it'll depend on the geometry of the problem. What's the guiding problem? Are there layers? Is it a free surface? All of these things will determine what's going to happen. So we're missing some information. We need some other information to allow us to find out what is the phase velocity, because to some extent that is indeed what we're looking for. Can we, yeah. If you look at the bottom 2 lines here, the basic statement is what we have not imposed yet is any boundary conditions on this problem. We have only formulated the dynamics. And these dynamics, this equation applies separately for every medium. So if you have 65 layers, there are going to be 65 A matrices, and each of the materials is characterized by its own set of gamma matrices. And in these problems, we always work with what I call rotated constants. Those matrices are calculated for each direction. You have to specify the direction before you can get these numbers. If you look up in the material tables, you will find these numbers given for only one standard orientation, the crystallographic orientation. If your device has got material layers with different orientations, you have to do that separate rotation of the constants to fit into your direction of propagation. This is relatively straightforward and well known, so I'm not going to deal with this problem at all. It's discussed extensively in the textbook by Old, and it's really a matter of doing some matrix pre and post multiplications, taking into account what are the angles that are relevant to your problem.
Dr. Adler,
Yeah.
question. Have we made any assumptions on boundary conditions, on the number of boundary conditions?
No.
Into 1 or more?
No, we have made a statement that there are 8 boundary conditions that must be satisfied at an interface.
Okay.
Between 2 materials. Okay? So if we have 2 materials in solid contact, then across that interface The stresses, the particle displacements, the potential, and the normal electric displacement must be continuous.
But the way we wrote the original equations of motion here, we're not making...
Nothing, no assumptions whatsoever. No, the equations of motion are vector equations. They're dynamic equations for an infinitesimal volume in the medium.
Okay.
The standard thermodynamic type of formulation. But it's a good question. We have made no assumptions as yet about boundary conditions, and I don't want to just yet. I want to continue and discuss the fact that we have an 8th order, in the sense that the matrix is 8 by 8 in the general case. This A matrix is 8 by 8 now for the piezoelectric medium. And so we have to ask ourselves from a system point of view, what are the implications of having an 8 by 8 matrix? By the way, this matrix J omega big A is the equivalent of the state matrix in system theory, for those of you who are familiar with system theory. It has 8 eigenvalues because it is 8 by 8, and there are a lot of statements that we can make about this. First of all, what do the eigenvalues of this matrix J omega A mean? They tell us what are the possible depth-dependent exponentials that can be constructed to form solutions. And you can think of these as being 8 modes, and they're of the form e to the lambda x3. The second point is, for each of these eigenvalues, there will be an eigenvector which tells you what the, quote, polarization of this mode is. And thirdly, at any location, any field solution must be expressible as a linear combination of these modes. Okay, so we have an 8-dimensional matrix equation, differential equation. It has 8 eigenvalues which tell you the 8 possible ways in which the wave can vary with the depth. And any solution or any value of the vector of 8 components can always be written as a linear combination of these modes. This is almost a copy from the type of things that you will find in system theory books. Now, let's take a look at the surface. Suppose the surface is at z equal to 0 or x3 equal to 0, then the x3 goes to 0 in this equation 5, and we can then rewrite this in a rather simple form as being some matrix times some vector of weighting coefficients. This P matrix, not to be confused with the P matrix of transducers, is the eigenvector matrix for the system. So when you find the eigenvalues of J omega A and you find the eigenvectors, then each of these eigenvectors, when you put them all into an 8-column matrix, so you get an 8 by 8 matrix, that's the big P. That's the big P matrix. And of course, depending on the software you're using to do the calculation, they usually come out in some specific order. And we call this the eigenvector matrix of JA. The omega is irrelevant because it's just a multiplying scalar. And so It just scales things up, and that's not important. The other thing that we know is because A is real, the eigenvalues occur in 4 pairs of the form alpha plus j gamma and minus alpha plus j gamma. The eigenvalues of big A, of course, must occur in complex conjugate pairs because A is real. However, because we've got a j multiplying it from out front, the structure of the eigenvalues is slightly different. And depending on how you formulate, you may like to do it this way, or you could do it differently. So here are our system, our eigenmodes, and these are the things that we know about the system now without doing any specific computations. And I'd like to go on to now our problem of main concern here, and that is what can we say about the half-space surface acoustic wave problem. So now we come to a specific set of boundary conditions, and we've just mentioned the fact that any value of this 8-component vector can be written as a linear combination and expressed in this form, which is equation 6b, where P sub p is the eigenvector matrix and yp is a set of weighting coefficients. And this is in particular the value on the free surface when x3 was set to 0. Now there's some critical things just above this equation which I really have to spend a couple of minutes on. On a free surface, if you're looking for guided mode solutions, you have to impose the constraint that as you go down deeper and deeper and deeper, the fields have to vanish. Okay? Now, because of the structure of the eigenvalues, which we just had a look at on the previous sheet, half of these will have a plus sign for the real part, and half of them will have a minus sign. So if the z-axis is vertically upwards, the only solution types which will decay with depth, which is the negative z-axis, are the ones which have the positive sign. Mm-hmm. Any of the negative ones will grow with depth, and so we have to discard them in constructing a solution. So this is then the value of this component on the free surface. Since it's mechanically free, the 3 stresses are 0. We can't say anything about the other components. However, we can break this up into 2 parts, what I call an upper and a lower part. So this will be 4 by 4, and this will be 4 by 4, and I only use those corresponding to decaying modes. It's very important, otherwise you're not solving a guided wave problem. Now I want to jump at this moment. We can write this in a different way. Look at equation 8. I can break this up into 2 statements by partitioning this into the first 4 and the last 4. And if you take a look at this is just the first 4 elements. You see that? And if I'm now going to jump, because I would like to finish off reasonably soon, I would like to jump and say, let's just look for a moment at the non-piezoelectric problem. The non-piezoelectric problem, this left side equation, D3 isn't there, we just have a bunch of zeros is equal to pp yp0. And so let me very quickly go on to the non-piezoelectric surface wave problem. Becomes very simple because you have a matrix times a set of weighting coefficients or a vector must equal to 0, and that only has a non-trivial solution if the determinant of the coefficient matrix vanishes. And so since the A matrix is a function of v sub p, phase velocity, its eigenvectors are functions of the phase velocity, and finding the solution to the surface wave problem is asking yourself, or computing, and finding what is the value of v sub p that will make this determinant vanish. Now that's a simple surface problem, and we use a numerical search in order to do that. I think what I will do is defer and start off next time from the multi-layered problem, and hope that between now and then you'll have had a chance to sort of think about what we talked about today on the one hand, and on the other hand there are two papers which were circulated as part of the reading material. Have a look at those two papers, because some of the things I will be talking about next time will relate to what's in those papers. One final thing, I don't know if this is going to appear. Let's see if it runs. This sort of looks like a double spike. Can you see it there? Okay, and that was, I ran lithium niobate, the determinant, as a function of the velocity, and you'll see that as you approach the surface wave velocity, the function value goes dramatically down, and if I take smaller increments yet, I can drive it down to essentially whatever value I need, things like 10 to the minus 30 or so. Well, I think that that's where we should stop today, and we'll pick it up next time when we start talking about layered structures. Thank you.